Alrighty, welcome back to 454. We survived the midterm, more or less. So they're grading it. I told them to grade it nicely. It should be pretty quick. It's meant to be graded quickly, so yay. All right, so today's lecture, I know it's right before reading week. This is mostly review, so if you want me to stop and do any of this in more detail, just let me know. I'm currently doing this in 3442, so I know this is all review. So this should be familiar, should be able to get through it pretty quick. There's one new thing that's not in 344, and then some other things that are in 344 that aren't here for some reason. So we'll just go through these slides, make sure we understand them all again. Let me know if you have any questions. We can come up with any examples you want. I have my virtual machine ready to go for you. So for this course, I guess where this is, so we are now done arguing about purely sequential programs. So far, single core, argued about, did a little bit of architecture, did a bit of compiler optimization, got a flavor of those two things, did some optimizations taking caches in mind, did some optimizations taking virtual memory in line, dynamic memory performance, all of that. So next is all about parallelization, which is what you have to do nowadays since every machine has multiple cores right now. So single machine parallelization that uses threads and processes on a single machine. If we get there, I don't think we really have all the hardware to do it, but you can have multiple parallelism going on between machines using some more distributed computing like, I don't know, Google's MapReduce or any other of the big distributed computing frameworks. So hopefully we can get to that. So this again should be review. So threads and processes, POSIX threads in particular, mutual exclusion and synchronization, everyone's favorite topics. So threads and processes. So everyone remember what a thread versus a process is? So process. Each process has its own virtual memory, open file descriptors, all that stuff. It, by default, runs a single thread. A thread is basically virtual registers plus a stack. And then all the threads live within a process. So a process can have multiple threads. If the process dies, then all of the threads within it die as well. So some parallel processing you can do with processes. So a web server or any other thing can do that because using one process is problematic. Client request comes in. This is mostly for everyone remember user threads and kernel threads. So I guess this is referring to user threads. So if you have to block in a user thread, it will block that whole process, any other thread from running. So if you have a bunch of blocking system calls, then the entire process gets blocked, nothing else gets to run. So if you only have user threads, you'd have to use processes so you can actually run multiple things at the same time. You can run other processes while you are blocked. So for this, they use multiple processes for service requests. The main reason you do that is because, well, if any thread crashes the process, then the whole process is dead. It kills any other thread. So things like Firefox and Chrome, they use processes for each individual tab. So if your tab crashes, the whole browser doesn't go down, only that window goes down. So you get some nice processes are isolated from each other. So they're nice in that respect. But you have to do inter-process communication between them, which is a bit slower. You have to do system calls unless you do shared memory and all that stuff. So let's have some concurrency. So again, that's just switching between processes. And ideally, we want parallelism. We want multiple things happening at the exact same time. If we have 4 cores, we all want them doing what we want, some useful work. So some server, a very, very naive server could just fork itself over and over again. Remember, that's the only way to create a new process. You fork, you create an exact copy of yourself, and then pass that there to independent processes. So the server could be blocking on connection request. Whenever it accepts a connection, it can fork. Then one of the new processes just deals with that connection, and that's it. So we should all remember forking and all of that good stuff. Everyone remember forking? Yes, it's forking fun. Haha. Oh God, I'm terrible. So a sample server could look like this. So I also have, this uses sockets, but same idea. Every web server basically looks like this. So while true, accept a new connection. So that gives you a new file descriptor that represents a connection between you and a client. And then you can fork return. I don't know why it's a capital F here. That's wrong. It's lowercase f. And then if it returns 0, that means you are the newly created process. So if you're the new created process, it closes the listen file descriptor. So that's waiting for incoming connections. And then because we only want the main process that is in this while loop to be accepting connections on that listen file descriptor. Again, I can give you examples if you want. And then here it would read and process a request, so just that file descriptor. Then it closes the file descriptor when it's done. Then it exits the process, so this process is no more. It's also missing a bunch of stuff. Everyone really remember 344? What is the state of the child process right after it exits? This is going back, huh? Is this a great program? Yeah.
Is that when they're a zombie?
They're a zombie. Yeah, exactly. We zombied it. So the child process here would be a zombie because it has terminated and we have not acknowledged it, right? Remember, we have to be good parents. So you have to do that wait system call to acknowledge it. And then you clean it up so that it does not become a zombie anymore and waste a process ID and some other space. The LOS can actually clean it up. So yeah, you can tell I'm criticizing this little block of code because we should be good parents, every one of us. So inter-process communication. So above, we don't have to communicate between the processes. Every process in that scenario just deals with one independent file descriptor. So if we need to do some communication, some types of communication we can do between the processes, we can send signals to them, which are basically like user level interrupts. That's also what happens if you hit Control-C and all of that fun stuff, or kill -9. Everyone remember how to violently kill stuff? Violently kill your orphan zombie children. Yep, those Google searches may come back. Pipes, so that's basically a shared region of memory. You get file descriptors, so you can write to one end of the pipe and then read data from another. And then through inheritance and forking, you can actually share file descriptors between related processes. You can also, which some of you probably haven't seen before, just share memory directly using the mmap system call. So that basically lets you modify your own virtual memory. You can request some virtual pages and set it so that whenever you fork a process, then it's actually pointing to the same physical page. If you change one of the memory address or values in one process, it appears in the other process. So they are now no longer independent because they are sharing some regions of memory. And this says how. Again, through mmap, you set up virtual pages so that they point to the same physical page. And the way you tell it, like part of the mmap system call, one of the arguments is whether you want it private or shared. If it's shared, then whenever you fork, it will not create an independent copy for that page. It will have both processes point to the same physical page. Therefore, you are sharing memory. Everyone's still good on board? Still review? So processes. So processes, you can think of it, they're made up of a whole bunch of different things. So a process context, CPU state, aka the value of the registers, and then an address space, which would be code, data, and stack, and then some other kernel state that the kernel keeps track of in a process. Things like the file descriptor table and some state of its virtual memory and what it can access. So the process contents will be like, data registers, stack pointer, program counter, also just registers, condition codes, things that are set on the hardware level, and then the kernel state, keeping track of its virtual memory. Its file descriptor table are the two main ones. And then here's a view of the memory. So your stack pointer is going to point somewhere to the stack. By default, your process will have a single stack. And then it'll map some region, some shared memory. And then BRK will point to the top of the heap. And the heap will start at some address that it just determines. And then before that, that's where your program gets loaded. So any read-write data, like global variables, things like that, the compiler just makes up a virtual address, and then the OS has to figure out how to place it in memory and map everything. And then there'd also be the code would be loaded read-only and execute, so you can't modify your own code. And it can share all of that code when you fork a new process through the magic of copy on write, if everyone remembers that. So, still good processes, still a review. All right, so some overhead. So creating a new process, pretty costly because you have to copy everything. It's not as costly as you might think because it doesn't actually have to copy all of the memory. It can do, again, copy on write, but still has to do a system call, still has to make a new process control block, still has to create a new process ID for it, and then it carries on its merry way. And then you have some overhead with actually doing IPC between the two processes because they require a system call. Although if you just do a system call to set up a bunch of shared memory and then use shared memory, it's actually pretty fast. So there's some overhead, but again, you can actually go ahead and make that quicker. And also switching between processes is fairly expensive, mostly due to flushing the TLB and flushing cache entries and having another process with a different address space come in, execute for a while, and ruin your perfectly nice and filled cache and ruin everything for you. While if you had a thread which lives within the same process, it uses the same virtual memory, so all your TLB entries are still valid. So a bit more expensive to context switch between them as well. So this is where I guess we rethought processes a long time ago. So you want them mostly to always share code and data. You want them to share some privileges like what file descriptors are open. And then maybe for the general case where you want to share most things, you want to make sure that they absolutely do not share like any of the registers. So wherever the program counter is, wherever the stack pointer is, all of its registers, and then each thing should also have its own stack space too. So that is basically what a thread is. You separate out the part that's important for execution from the other part that has to do with memory and all of its other state. So the execution state, basically just how to execute it, is just called a thread. So it's just registers, and then each thread needs its own stack because it needs to essentially run C code and use the stack and all of that. So from this, what it looks like is, well, in kernel space is the kernel, and then in user space, you have processes, which are all controlled by the kernel. By default, each process in a circle here has a single thread in it. But if you go ahead and separate it out, you could have one process with 3 individual threads in it. They would all access the same memory. They all share most things by default. The only things they don't share is anything directly related to only execution state. So good like that. Still good. All right, perfect. So a process with 2 threads, well, the thread context, again, they'd have their own independent stack, and then their own set of registers, and then everything else will be shared. All of the heap variables, all of the global variables, everything like that. There's only one of them, so they're all shared between all the threads. The only thing that would not be shared is the stack. So the stacks are visible to each process, or sorry, to each thread. But if you give away an address to your stack, you're probably screwed. So you have no idea how that other thread is going to execute. You shouldn't depend on its stack. You can actually access its stack if you have screwed up. but it should be the case that their stacks are independent. So if you start giving away addresses to threads, to other threads, you are, there's no one to blame but yourself for your now 21-day debugging journey at minimum. So processes, averse thread, so they all have their own execution. They all run independently, concurrently, or in parallel with others if they're kernel threads. The only difference is by default, threads share everything within a process, and processes are completely independent of each other unless you essentially opt in to not be independent. Threads are the other way around. They are all sharing all resources unless you opt into not sharing. So that is the major difference between them. So if you have a thread-based design, really easy to share structure, like any caches, anything like that, they're more efficient, they're easier to set up. You only need something to keep track of the registers and the stack. So they can be, in this case, on some server, can be like up to 10 times faster to create. But sharing by default, that has to do with data races and all of those really fun to debug things. So each thread, since they're shared, it's really, really easy to mess things up, get in the situation where you have data races and then you have really, 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 really hard to debug things because things are no longer deterministic if you have multiple threads running and you don't know what order they're going to run in. So POSIX threads are what we'll use and what everyone uses on the planet. So everyone should more or less remember the interface. So to create them, basically you create this pthread_t. You can think of it as a thread ID. It's really basically just an int. You pass it by pointer to the thread create function, so it will assign a value to it. So it'll dereference it and then assign you a value to it. Then there's some attributes here. You can just say null if you want the default ones. And then a function to run, which the whole prototype is gone from here, but it's a function that takes a pointer and returns a pointer. And then this arg is the value of the pointer you want to pass to this function whenever it first runs. And then by default, threads are joinable, which means when a thread exits, it becomes like a zombie thread, right? So it keeps its thread ID around, and in order for the OS to clean it up, you have to join it. So to join a thread, you join using its ID, and then you get a pointer to a pointer thread return, so that will just write to that memory location the value that this function returned. So it will return a pointer, it'll write it to that location. So that's why it's a pointer to a pointer, because it'll dereference it and write a pointer value there. So anyone remember, if you don't, almost swore, if you don't care about the return value of the thread and you don't want to join it or anything, anyone remember what you can do to a thread to say, I don't care, clean yourself up? Yeah. Yeah, you can detach it, right? You can have detached threads if you don't care about the return value. If you don't care about joining them, you just want them to go ahead and clean up all their resources. When they exit, you can just detach them, which I don't think is here. You can also determine your own thread ID. pthread self will just return the ID of the current executing thread. So for terminating threads, you can essentially cancel it, which basically is like the process equivalent of sending a signal to it. So it will immediately terminate and stop running. Usually you don't have to do that. And then you can exit prematurely. So you can just do pthread exit. That will exit from the current running thread. It exiting from that run function will implicitly call pthread exit, which I guess is what that was supposed to say. And then that exit system call, well, that's by default what happens when you return from main. The return value gets passed to exit. But if you just call exit yourself, that's exiting the process, and that will terminate every single thread running. The process is now dead. You can't do anything about that. And then we'll also see, I don't know why this says later, we'll see it probably today because we are zooming through this. So everyone's still good? Everyone still remember? All right, so thread creation. So we'll have a main thread initially running the main function. Then if you have pthread create, well, now two things are executing. You don't know what order they're going to execute it in. One thing is going to continue running main. The other thing is going to run the function that you gave it. You don't know what order it is going to run in. It is up to the kernel scheduler to figure it out for you. So if we want to join threads, this is what it will look like. So we have a function to run. We create a thread. Here, oh no, we give the address to our stack location, but this one's okay because we know that this variable lives longer than the thread because we join it after. So this is one of those rare cases where it is okay. So it gives it the address of X, it does something with it, and then the main thread joins it, and join is essentially like, for processes, it's the same as wait. It will wait for that thread to terminate before it actually returns and then continues on its merry way. So we'll know that the thread specified by ID has been terminated now. It is not a zombie thread. It has been cleaned up and all that good stuff. So this is how the join looks like. So we create two things. The main function keeps on executing. The other function running in the thread can run. You don't know what order they're going to run in. If the main thread runs first and it hits join before it terminates, it would block. It can't run until that thread actually terminates, and it will terminate whenever it returns from its run function. So it would have a return null in there, and then the main thread would finally unblock and then continue on its merry way. Could be the case where function runs first, the thread dies, it terminates before main even starts executing, and then whenever main makes it to join, it would immediately return from join because that thread's already done. Order doesn't really matter in that case. It will only pass join whenever the other thread is terminated. So this is a pthread hello world. Everyone okay with this? So, again, not sure why this is here. This should be completely reviewed. So, if I run this, what happens? Goodbye world. So, should print hello world how many times? Once. That's it. I don't know what else to do with that. So just prints world once. Anything I need to explain here, or is it all right? So the only other thing is for join. If I don't care about the return value, I can just give it null, and that says I don't care. Don't try and write anything there. I don't need the return value. So how to properly program with it? Well, I need to first, the most important things for this course is I have to decide, what I can actually run in parallel. And then, well, I have to create some threads so I can actually run the thing in parallel, and then have to argue about data races, prevent data races, and add some synchronization code to make sure that data races do not happen. I also might require some synchronization if there's any happens before relations, like I need a whole set of operations to finish before another set of operations. So this is something you'll get some practice in this course, hopefully. If not, I'll add some more stuff. So we should know some things. Data races, we usually use mutexes, and then for ordering, we can use things like semaphores, condition variables, and something new we'll go over again, and then something new called barriers. But there's some problems where you don't have to worry about it. So if I have a matrix multiply again, so something like this, well, this is something called an embarrassingly parallel problem because I can easily separate it out to as many independent calculations as I want. So if I have 4 cores, I can just have each core do a fourth of the work. And here, the work would just be assigning to this C value, or this, C index in this 2D array. So I can have just one core calculate a whole, like a fourth of the values. And that is okay because each thread would be writing to its own independent location. I don't have any problems with a data race because a data race, two concurrent actions to the same location with at least one being a write. So if I divide it up, have each thread do a fourth of the work, then each thread is writing to its own unique memory location. I don't have a data race. And then all the other threads would have some overlapping information with accessing the A and B matrix, but it's okay. They only read from them. They never modify it. So I'm free to share it. So this is the easiest way to parallelize something, and you get basically a perfect speed up. If you have 4 cores, it goes 4 times as fast. Each core just does a fourth of the work. If you have 16 cores, each does a 16th of the work. It goes 16 times faster. That is something we call embarrassingly parallel. And there's some research to do this automatically. Has anyone in this class used OpenMP before? Nope. Okay. So OpenMP is just a way to use threads a bit easier. It uses pragmas everywhere. So if you want to make a for loop, divide into 4, you can just do like pragma OpenMP parallel 4, and then it will just run that for loop in parallel, divide it up for you so you don't have to bother doing it for you. So just a nice way to, well, an easy way to do some embarrassingly parallel things, which we might see later. I don't know if it's currently in the course, but it doesn't take that long.
Is that a library, or is that a...
Yeah, it's a library.
So nothing special. It's just going to spin up like a queue for you and a bunch of threads.
So it's basically just going to manage P threads for you.
Like, cool. Basic edit. Oh, that's really cool.
Yeah. So that's called OpenMP. It's just a compiler flag. Most compilers support it. So if we have parallel matrix multiply, well, we already saw how we divide it up. And what we would do, we just create a thread, give each thread an index. In this case, this case is bad. This case is really bad. So also it's missing the declaration of I. I don't think no one actually ran this code. So this is missing the declaration of I, and we're giving the address I to a thread. I think this one should show the error, but this is a bad thing because it's going to change the loop variable every time. There's no guarantee that when the thread actually runs, it is the same value of when it's created because the main thread is constantly changing it all the time. So if you write something like this, I will be very disappointed in you. So what they should have done is like just malloc some space for it, write the value there, and then pass it by pointer to the heap. And then each one has its own independent pointer to some memory location on the heap. So the matrix multiply, if you successfully give it the ID, which this will not work, this definitely has a bug in it. But assuming you got a correct ID, which is 0 up to the number of threads, then you just calculate your slice. So this is just the bounds of the loop to get your 1/n part of the loop. So that is just the calculation you do, and then you have each thread do its own independent part of that calculation. So some other things you can do. You can have a manager worker, so the manager performs setup, partitions the work. There's a whole bunch of libraries for this, like thread pools and things like that. So the manager just manages a whole bunch of like tasks and then makes some threads that will actually perform the task, and its job is to say which thread runs which function. So this might be a bit easier than using threads yourself. You just define a function as normal, throw it in there, but you have some shared state. You can't really argue about what's running at any given time or what gets scheduled on any thread. So it's easier like the workers run some stateless function or something like that, so you don't actually have any data dependence on it. So it's a lot, you don't have any dependencies, so you can just run them in parallel, it doesn't matter. Because yeah, it's typically, if you have to enforce job ordering, then you're in for a world of hurt where you probably should just spin up your own threads and synchronize them yourself. So other things you can do is you can have some pipeline execution. This is basically creating pipes between two processes. So a pipe is basically a buffer. One process writes to it, the other process reads from it. So this is a cheap way to do inter-process communication, and the processes could also run in parallel depending on the data. So it could send a line. These programs could be running at the same time. So whenever this writes a line, this reads it. It could be done in parallel if you have multiple cores. So the processes don't share any state. They only communicate by just feeding information to each other. Each individual process is single-threaded. It can deal with its own state, doesn't have any data races, only has a single thread. Everything's ordered, so it has to, the information has to go from process 1 to process 2 to process 3. Simplifies some jobs. Some things, I mean, it's easier if you just have a set dependency order just to do this. But code is written in some callback style. It's hard to debug. I can't send messages back up. They only go one way. They don't go, like I can't send a message easily from P2 to P1. I can only send messages from P1 to P2. And if anything goes wrong, it's hard to tell which process actually had an issue. All right, mutual exclusion. So this should be mutexes. So mutual exclusion. For some reason not mentioning data races. So if we want to prevent data races, 2 concurrent accesses with at least one being a write. So if we want to prevent data races, well, we can get rid of the 2 concurrent accesses part and make sure only one thing writes at a single time. So if we want only one thing to write at a single time, we can put that code in something called a critical section. And the critical section only runs one thread at a time. Only one thread can be in that critical section at any given time. And you would do it with a mutex. So you lock it. After you lock it, there's only one thread that can pass lock at a given time. So only one thread is in this critical section until it unlocks, give up the lock, and then another thread can actually go ahead and execute that critical section. This does not give any guarantees on ordering. This is only to prevent data races. So ordering would have to be something like a semaphore. So for mutual exclusion, it works independently of the speed of the threads. Like anything outside the critical section can run in parallel. So hopefully your critical section is small. And then other threads trying to enter the critical section will eventually get into it. So hopefully, like I said, the smaller your critical section, the better you'll be, because essentially the critical section just runs in serial. So only one thread can run it at a time. If you are old school Python that has a global interpreter lock or anything like that, all the Python interpreters basically runs in serial. So that's why Python threads historically don't do anything, because they're all blocked on the global interpreter lock, although I believe in Python 3.12 it's now gone or greatly reduced. So Python threads, I believe, slightly work now, and you can get some good performance. But before that, in Python, if you want things to go faster, you can just create a new process. You can just fork it and carry on. So for mutual exclusion, so the more, like I said, there's only one thread that can run the critical section, in this case the red part, at a time. The other threads block if they make it to it while some other thread is in it. So the critical section itself, only one thread at a time, and the time other threads are spent waiting on it, they just get blocked. They're not actually doing anything useful, and it will hurt your performance. And in fact, locks aren't free, so there's some overhead of calling lock and things like that. So if you do this really, really poorly, you will make your program slower than if you just didn't use threads at all. So that's called coarse grain locking, global lock. So global Python, the global interpreter lock, that just means basically you just have one big lock around everything. Only one thing can run at a time. So why did you bother using threads in the first place? Everything will be slower than if you didn't do this. It's an easy thing to do to prevent data races, but again, your performance will probably be worse than if you just didn't bother to try at all. So, really slow. So fine-grained locking, hopefully you make your critical sections really small. To prevent overlap of locks, you can use different locks. So if you had two different locks, an A and a B, then, well, slightly better, because threads could run A in parallel with any critical sections of B. So both could run at the same time. But again, you have to make sure that there's now no data races between critical section A and B, since they can now run in parallel. So main thing you want to consider with locks is contention. That's basically when a lock is held by another thread, basically how many threads are fighting for a lock at any given time. Ideally, the number is 0 or close to 0 or 1. You just want it for the rare case where it is unsafe to run in parallel, and hopefully you make it as small as possible. Because, well, scalability, that has to deal with how you scale with multiple threads. So the ideal scaling is 4 threads, 4 times faster, you get linear scaling. So the more locks you have, that's more serial, that's more section that's serial, you want to reduce that as much as possible. So the only problem is, well, yeah, the coarse grain locks you have, you'll have more contention, it's a bigger space, and also you'll have some unnecessary cache misses. We will probably get into how caches are consistent when we have multiple threads running at the same time, modifying values, making sure that things happen atomically. So we have to keep all, you might imagine from the architecture point of view, it has to keep all the caches of multiple threads in sync, which is easier said than done, but we might see some of those fun caching protocols. Although again, they should probably be in your architecture course. And because of this, all the cache, trying to synchronize all the caches and all of that as well, that can also put strain on your caches and make your performance even worse from single core from another fact. Not just the overhead of the lock, but essentially destroying your caches again. So for the Linux kernel, OSDI 2010. So the kernel back in the day, I guess kind of similar to Python, just had a big old global lock. They called them big kernel locks. And they finally got rid of it in 2010 because, well, multiple core machines were not that common, so they didn't care. It was just to go ahead and prevent any data races in rare occasions. So whenever they took it up, the report core throughput shot up through the roof from just that one change. So like Apache, which is mostly embarrassingly parallel. Well, before, when there's a big kernel lock, any system call would essentially be serialized, and it mostly does system calls. Think of a web server. All it does is communicate to a client. So it pretty much only does system calls. So, of course, when they removed that, big performance increase. But again, you guys don't have to worry about that because we live in the year 2024. So this has been removed for quite a long while since we're on, what kernel version are we on now? Like 5.12 or something like that? I forget, something like that. So there's also other big caches. So Facebook memcached, basically it's a web server cache that caches any like API requests and things like that. How it works is they had a big lock to protect shared data structures. It's basically more or less like a hash map of a whole bunch of different data. So they had one big lock to protect all the data and then fine-grained locking for each individual nodes. You guys didn't have a lab like this, but one of the labs I have is like parallelizing a hash table. You can have a big lock around the whole thing, make it safe, but it goes slower. So you can essentially just have an individual lock for each of these like linked lists, and then you reduce the contention, have more fine-grained locking. So, hey, we finally got to races here. So data race, when certain thread interleavings lead to incorrect program behavior, but I like saying it as data race, two concurrent accesses to the same memory location with at least one being a write, which means you have to protect the read as well, otherwise you might get inconsistent data. So that is, again, what a data race is. That is the primary concern to make sure your application actually behaves as you expect it to. You want to eliminate data races at all possible. There are some tools like thread sanitizer, things like that, that will help you catch data races. But past that, you have to just program carefully. So here is a data race example. Funnily enough, it is the previous example as well that just now defines I, gives each thread the address of I, and then changes it again through this loop. So now when you don't know when the thread's going to execute, it's just going to read whatever I points to. The main thread keeps on changing the value of I over and over and over again. And it's still alive when the other threads are alive because it joins all of them. So it's going to read some value between 0 and less than n minus 1, but we don't know exactly what they're going to be, right? So if I ran this, I have no idea what will happen. One thing that could happen is this: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, so if I create 10 threads, that means I will go from 0 to 9, but each individual thread may not read the value that I was when it was created. So in this case, I guess it assumed that the two other threads read the last, didn't execute for a long time, even though they printed before the other ones. I guess they just didn't read that variable first. So they didn't read the variable. The main thread actually came here and blocked and set, and I was equal to 9. And then the other ones read it, although one of these threads should read 9, right? The only thing that was wrong is one of these should be 8 instead of 9. But this is one of the outputs you could get. You could technically get any numbers here because you have no idea what the hell is going to go on. And again, alarm bells should always be going off if you give one of the addresses to your stack away to another thread. You should immediately start screaming. You have permission to scream at whoever did that. If you ever have to do a code review at a company and you see someone that does that, see if there's like a company bat to hit them with or something. Like, that should not happen. So for synchronization, so that means we want some type of ordering to preserve some dependencies. Mostly happens before dependency. So one thing that you may have not seen before is a barrier. So a barrier, they're really common for GPU programming. That's really the only synchronization you really use. That makes sure all threads wait at the same point in the program. Basically, it's like doing a join for all threads, but with a barrier, you can set how many threads you want to arrive at this barrier before you continue. And then we could have a producer-consumer example where thread A is waiting for stream examples, thread B is reading them. So one's writing, one's reading. Could have multiple readers, multiple writers. Doesn't matter. You could also use condition variables to wait for an event to occur. Condition variables, basically, they're just like a queue that you can manage yourself. So this is what a barrier looks like. So it will block a process from the time you arrive at the barrier until you leave, and you can only leave a barrier when all threads have arrived at it. And as part of creating a barrier, you say how many threads have to arrive of it to be considered everyone has arrived, and you can continue. So in this case, we can create a barrier that waits for 3 threads to arrive. Let's say thread 3 arrives there first, so it will get blocked. Then thread 2 did some useful work. It hit the barrier, it gets blocked, and then thread 1 hits the barrier, and then it takes a little bit of time to wake up all the other threads, and then they have now all arrived at that same point. That would be your synchronization point. You know they're all there. So if there's some dependency where all these threads have to do something that happens before they do something else, maybe some calculation or something like that, that's your synchronization point. You know they have all arrived at the barrier, they have all finished what they were going to do. More common if you do GPU programming, which hopefully we will see. So how you use a barrier, well, it's just called bthread or pthread barrier T, and you can just set the attributes to null, so it's just the address of the barrier to initialize in the init, and then the unsigned count, that's how many threads you want to actually call wait, this barrier wait, until they actually continue. So it will wait for that number of threads to actually arrive there. So you can set that to whatever you want. So condition variables. So they require a lock. The way I like to think about is a condition variable is basically a queue, and it needs some type of mutex so that it makes sure that there's no data races with the queue, and it has to do some fudging so that whenever it can like add itself to the queue and give up the lock before it actually goes to sleep and blocks. So how to create a new condition variable, pthread cond. There's a typo here. This should be cond, not saying that. So this should be cond. You init it, default attributes, and to destroy it, if you init something, it's like mallocing, you should free it. So the pthread way is to destroy it. So how the condition variable works is to actually put yourself in the queue and wait on something. You have to have acquired the mutex, so you've had to successfully return from locking the mutex. So you have to hold the mutex, and then you can do con wait. So that will put you, again, I like thinking of this as just a queue. It will put this thread in the queue and block it, and also unlock the mutex as part of that. And then whenever it wakes up, it's going to reacquire the mutex before returning from wait. So before the call, you have the lock, and after the call, you also have that lock. So if you want to unblock a thread, which is currently in the queue, you use signal. That will unblock the first thread that is at the head of the queue. If no thread's waiting, it does nothing. And then if you want to wake up every single thread that is in the queue and have them all fight over that lock, you can do broadcast. So that will wake up everything in this queue. And for signal and broadcast, you do not need to have the mutex acquired to call these functions. You can just call them, don't have to have the mutex acquired. So to parallelize this code, if you had something that wasn't embarrassingly parallel, so you have a write to index I, and then you have some long code that actually reads from a previous value later. So what it looks like is, hey, I'm writing to 3, but in the future, I'll be reading from it. So I want to make sure that this happens, this happens before this happens, assuming that I want the most up-to-date version of it. If I don't have any synchronization, I won't have any ordering between the threads. So I don't know if I have the most up-to-date value or not. It's complete chaos if I just try to parallelize this code, thinking it's some embarrassingly parallel thing, because there is dependencies between loop iterations, which would cause dependencies between threads. and cause data races. So one way to try and solve this is to use a condition variable. So if all the writes have to happen before the reads, well, I might just signal, like create a condition variable for each iteration that will go ahead and make sure that the write has happened before the read. So I could signal that would wake up anything that, well, typically you place the wait first. So I place a wait here that if I make it here, I put myself to sleep and then waiting for this value to get updated. So this would be using that same index. So I would have another thread signal whenever it's done updating that value so that I hopefully wake up and then I can go ahead and use the most up-to-date value. But the problem with this is, well, since I don't know the order of the threads, it might be possible, like I only call signal for every element exactly once, right? And I only wait exactly once. So it might be the case where I signal something and that queue is currently empty, in which case it won't wake up a thread. And then if that thread then executes and makes it to wait and it blocks itself, nothing's ever going to wake it up. It is now essentially in a coma, and then it's never going to wake back up again. So this is not precisely what we want. Also, you could consider that a form of deadlock. It's not going to wake up. So one thing you can do is try to remember a signal. So we can make this more complicated, and then for every index, we can see if a thread has arrived there now. So we might, since we're sharing indexes, we're writing to the same location between threads, we need to prevent a data race. So we need a mutex for that number, or I could just make it atomic. But in this case, I guess I just assume that I only have a mutex. So I have a mutex to protect that array index. I create a new array that indicates whether or not I have arrived there yet. If I have arrived there, I can go ahead and signal that thread, unlock it so I don't have any data race. Otherwise, for my wait, I can just make sure that, hey, I'll only wait if the signal hasn't happened yet. So if someone's already been there, then, well, I don't even have to bother waiting. I can just go ahead, continue. I can skip over the wait, and then I can just reset it for the next time. Although this time, I probably don't need to reset it. But in general, you could reset it if you have to iterate over the array a few times. So that is one way you can fix it. Another way you could do that is just with centerfors. So a centerfor, basically, it is an unsigned integer, and it has two atomic operations. It has a post, which will atomically increment that value, and then a wait, which will atomically decrement the value. And the only catch is the value will never go negative. So if the current value is 0, it will not decrement it. It will wait for another thread to atomically increment it before it decrements it, and it can go ahead and continue. So kind of works, well, there's an equivalence between condition variables and centerfors. You can implement one with the other, but some things might be easier to read with centerfors as opposed to condition variables. And here, post, that's the equivalent of up, that's incrementing it, and wait's the equivalent of down, that's decrementing it, and if it's 0, you wait. So producer-consumer problems. So you can use threads to communicate with each other using a shared buffer of fixed size, like a bounded buffer that just, or a circular buffer that just writes over itself over and over again. Your producers fill the buffer, your consumers empty the buffer, and then you essentially have two synchronization conditions. So producers should wait if the buffer is full. So those are the things writing values there. If it's already full, they should just wait for a consumer to empty out one of the slots. So consumers should wait if that buffer is empty. So this is how it could look like. You have, don't know why you have 7 usable slots. It should be 8. It's of size 8. not sure. And then you have all of these are all shared variables, so you have all of the producers sharing an index where to write, all of the consumers sharing an index where to read, and how it works, this is basically just a circular buffer. So you have to make sure there's no data races with this index between all of the producers and no data race between this index between all of the consumers. So the consumers will just write at an int or write at in, increment it, go clockwise. It's a circular buffer, and consumers will also read from the same thing. So if there's a filled slot, it should read from it. If there's no filled slot, it should just stop and wait for data to come in. So the number of elements in the buffer, well, you can just count how many are used, like the difference between the in and the out. So in this case, how it's shown, then there would be 3 used slots that have data in it. So the buffer is full when you can actually have it full if it's completely full of all individual elements. You don't have to do an off by 1, and it's empty if there's absolutely nothing in the buffer. So how it would work with condition variables is something like this. Do you want me to go over this in painstaking detail?
Yes.
Yes. All right, actually, so there's with monitors, which they call condition variables, or consumers. Funnily enough, I'm actually doing this today in 344. So I can just use my same virtual machine. So here's our producer consumer. So we can warm me up for later today. So here is the producer consumer. So I have written a program, I can share it with you if you really want, so it uses the semaphore to keep track of like just internally how many things I want to produce or not, because it's atomic. Don't worry about it. Just assume in a real thing this would just be while true. The consumer would empty a slot and then simulate it doing some work on that element. And the producer, well, it would be an infinite loop. It would simulate some work to generate that number and then to finally fill that slot. So I basically have 2 instances of a data race here, and assume that this fill slot and empty slot, they all share that index. I protected it with a mutex so there's no data races or anything like that. So if I run this right now, the 2 really bad things that happen to this buffer is I could fill an already filled slot. So I overwrite a slot that was never read from, which is bad. That means I have destroyed some data. And the other bad thing that could happen is I could try to read data from a slot, empty a slot that's already empty, right? 2 bad things that could happen. So if I run this, so I have it set up that I can specify the number of producers and consumer threads, and then the number of elements to produce. Currently it's just 15. And then the size of the buffer, currently it's just 10, so it's a bit smaller. And then I can adjust how long it takes to produce an element and consume an element if I really wanted to mess with them. But initially I can do something like, let's say I have 10 producers and 5 consumers. So if I have something like this, I have no ordering whatsoever. If I run it, I have it printing off what happens and then printing in red if anything bad happens. So when they start, if I don't have any ordering whatsoever, my producers will be producing work. So they're working, hopefully doing something useful. So if I don't have any ordering, my consumers immediately run, right? Which would empty a slot that's already empty. So since I have 5 of them, they would all run in parallel. So I empty out 5 slots that are already empty. And then they're doing some work. Then eventually the producers are done. So those 10 producer threads fill every single slot, right? Oops. So they fill all 10 slots. They fill up the buffer. And then, well, my 5 consumer threads, they now get a bit lucky because they run again and they go to the next 5 slots, and there's actually data there for now. So yippee, my program read something correctly, so that's great. Then my producers run again, and then these are the last 5 data slots, but they overwrite slots 0, 1, 2, 3, 4, and that's bad. And then finally my consumers finishing the last few elements they think, which would get correctly slot 0, 1, 2, and 3, which just got overwrote. So everyone good that that's bad. All right, so to fix this using semaphores, help. So there's some type of ordering between that I should do. We got 40 minutes. So for me, the thing I like to think about first is, if we haven't reviewed this before, so semaphores, usually you have to place the weight, you have to place the post or the increment, and you have to set some initial value. So I always find it easier to think about, okay, the easiest thing to place first is the weight. Like, what do I have to wait on? So in this, there's 2 things I have to wait on. What's the first thing we want to wait on? Slots to be filled. So we want to, or which error message do we want to get rid of first? So slot is already filled.
Before you empty a slot, you need to make sure it's previously been filled.
Oh, okay. So we're going to make sure that when we empty a slot, it's been filled, right? Okay, so that's probably the easiest wait. So I should place my wait right before that empty slot here, right? I want to wait until there is some filled slot before I try to empty it. So I should probably do some wait, and then, oh, okay, I need a semaphore. So let's create a semaphore. It's called sem_t. Can give it a name. Let's, in this case, we only want to empty a filled slot, right? So I should probably call it, I don't know, let's call it filled slots. So if I call it filled slots, then I am now waiting on it here. So I'm waiting on the address of filled slots. All right, so next thing I need to do is initialize it with some value. So for that, we do sem init, give it the address of filled slots. That's my semaphore. Next argument is p shared. So that's what happens to the semaphore when I fork. If I set it to 0, it's not shared between processes. If I set it to 1, it's shared between processes. So you can use it to do some synchronization between processes if you really want. But of course, you'd have to fork and all that. So I'll just give it a big fat 0. And then the next one is the initial value. So the initial value, the way I like to think of it is the initial value is how many threads can pass that weight initially. So how many threads should pass this weight initially? 0, right? I initially don't want anything to write, so I should just set it to 0. So now the next thing I want to do is essentially place the post, which is basically saying, hey, what is the action that will let one thread pass, or one thread wake up and actually get through its wait? So where should I place the post? Yeah. After the fill slot, right? After I fill up a slope, I can actually do the post here. So that will increment it. In this case, if it's the first slot, increment it from a 0 to a 1. And then that would allow one consumer thread and exactly one consumer thread to actually unblock from this wait. It would actually empty that one filled slot, right? So filled slots. Whoops. Sem post. All right. Everyone in agreement with that? That looks good? All right. So if I run this now, let's check our work. So I should, oh, see, I've run it now, and I'm done, right? So I get no red marks. Am I done? Am I God's gift to programming? No, right? Because what's the condition? So what should I do so that I see some errors happening? How many consumer and producer threads do I need to see something bad happen?
Just run more cycles.
Run more cycles? Like just have more, so this, and just more numbers, like 100? Yeah, that worked. So that'll do it. Maybe if I have the other way around, oh no, the other way around doesn't work. 1. Oh no, there's way too many, right? There we go. So if I have way too many, what is this? If I have way too many producers and only one consumer, well, my producers just all go and overlap, and then eventually I'm emptying a slot that's already empty because essentially my producers overwrote themselves eventually first, right? So I filled a slot that was already filled. So for these, you should look at the first error you have, and that's the thing you need to fix. So I did empty a slot that was already empty, but my first error that caused the whole thing was filling a slot that's already filled. So in this case, I probably need a new center for. Before I think of a name for it, let's place the weight. So what am I waiting on? Or where should I place my weight? Yeah. After the empty. So here, whoops. Some weight. Before the fill. Yeah, so probably before the fill, right? Because I don't want to fill a slot that's already filled. So I want to put my weight before the fill slot because I'm trying to make sure I don't fill a slot that's already filled. So if I'm trying to wait for if I don't want to fill a slot that is already filled, I only actually want to be filling empty slots, right? So that probably gives me a good name for this new center for, so I'll call it empty slots. So I want to make sure that I wait essentially for an empty slot. All right, so then we come to our init. So now the next thing I like to do is think of the initial value for it since we have now placed it. So what should the initial value be, or how many producer threads should be able to go past that weight initially? Buffer size, right? Because after that, I start reusing the buffer. It's a circular buffer, so I can fill it, but as soon as it's filled, I need something to empty a slot before I continue filling it, right? So luckily, I have the buffer size as a variable, so I can just initialize it to the buffer size. All right, so I'm missing one more thing. What am I missing? Yeah. Yeah, the post right after empty. So if I empty a slot, that means I should post up empty slots. Oops. Right? So if I run this now, it should work flawlessly. So that was the first one that was really bad. So if I run this now, boom, no red. If I run it with, I don't know, 100 different slots, should just keep on going over and over again. I have way, 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 way too many producers, so, and only one consumer, so that's why it's immediately filling. If I even it out a bit, so hello terminal, thank you. If I even it out a bit, where I at least have 5, I'll probably be running more or less in parallel 5 at a time. depends on the number of consumers and producers I have, but it all works. So everyone good with that? We have solved the producer-consumer problem. Yeah.
Under the hood, is a semaphore just an atomic?
Yeah, yeah, it's basically an atomic. Well, the post is an atomic increment. The weight is like, yeah, it's an atomic decrement, but it will also do that thing where if it's 0, it just blocks. So there's some other logic there.
Yeah, it's a condition variable packed in with it, right? Which, like, it has some queue, keeps track of the threads that are waiting on it, and will wait other threads specially, right?
Yeah.
It has to know exactly what.
Yeah.
it's like.
Yeah, so you can rewrite semaphores in terms of condition variables and condition variables in terms of semaphores. It's just whatever is clear for the application.
The mutex is usually just an atomic in that way.
Yeah, let's see. Do I have the other example, producer, consumer? I guess I don't have it. So you can also do this producer, consumer with condition variables. I believe I have an example in my 344 slides. But it'd be the same thing, but instead we'd have to, if we use condition variables, like we would just have like an int keeping track of the number of filled slots. And then here we would check if all the slots are already filled, then we would put ourselves to sleep, we would wait. And then in the consumer, if the number of filled slots is 0, then we go ahead, we put ourselves to sleep. And then you would, like the post, you just put a signal after you have emptied a slot to wake up some thread waiting for a filled slot. So, any questions, comments, concerns, or we can end early. It's reading week. Yay. Yeah.
In general, would you say semaphores and CVs, when used appropriately, are more performant than mutexes?
Different applications. So typically you use semaphores and condition variables to ensure ordering, and mutexes only to prevent data races. So typically it's a little of both. So like this fill slot, this, I didn't show it to you, but fill slot uses a mutex because all the threads share that common index. So that is a data race. Unless I use a semaphore as a mutex, I need mutual exclusion so I don't have data races. So it's usually just using the right tool for the job. Preventing data races, boom, mutex. Having some type of ordering, semaphore, condition variable. One's equivalent of the other, it's just whatever looks clearer for you. So usually if it's just keeping track of the number of things that should happen, semaphores are easier. If the condition is way more complicated, then, well, they named it condition variables for a reason. All right, yeah?
I'm a little confused. So when you post, you increase the semaphore value, and
Yeah.
then it decreases when you wait?
Yeah.
Okay.
Yeah, weight atomically decrements it, and if the current value is 0, it will wait for it to go positive before it unblocks something. So you're guaranteed it's all, and it's an unsigned int, so it can't go negative. All right, any other questions, comments, concerns? Happy reading.